Hello. This is the first half of the final part of our design discussion. Now, so far, we've discussed everything under 4 here, meaning review 4, design tools and testing. We went through a whirlwind introduction to UML class diagrams. We've spoken about and discussed proper object-oriented design and analysis. We had our design the CS250 way discussion that took us through the examples 1 and 2 and 3. And then we left off on 3, and I want to revisit that one very briefly before we get started here. And what we're going to discuss now is this last section here, testing in C++, JUnit, and PyUnit. And I'm going to come back to just why we are going to discuss all of those and why they all relate to one another. Now, this says examples 4 through 6. We're going to start with example 3 very, very briefly. Now, what I do want to discuss before we get into any of that is right here with the class checklist. And it would help if I click the correct link. Now, a few discussions ago, we talked about the class checklist, specifically the C++ class checklist. Then we moved into the Java class checklist and the Python class checklist. And the crux, the major point of that discussion, the major thing we took away from that is this class checklist is not an arbitrary set of rules. It is a set of rules that emerges by the very virtue of object-oriented programming and design and what we need to do when we define our own data type. Meaning, when we define our own type, we need to be able to initialize it. And that's where our constructors come into play. The default constructor when we create one without any input. We need some sort of copy operation, be it a copy constructor, a clone function, or a deep copy function, to take a piece of our existing data and make a copy of it, a deep copy guaranteeing that all the data in both those copies, while it is identical, they are in fact distinct copies all the way down. Then we have a few exceptions in the middle. Then we get to accessors and mutators, meaning functions that allow us to examine the state of our object and change the state of our object. Now, in the context of getters and setters, meaning functions that allow us to retrieve and examine our private data members, and functions that allow us to change those private data members, those translate one-to-one throughout all 3 of the languages we have examined so far, C++, Java, and Python, specifically Python 3. Now, for the remainder of this discussion, anytime I say Python, you can assume I'm talking about Python 3. Now, probably one of the most straightforward functions to see coming through all of these is the logical equivalence operator, meaning equals. When we have 2 objects of an arbitrary type, we need to be able to check and see if they are equal. For integers and real numbers, that's fairly well defined. We've done that in math. 7 is equal to 7. But that's less defined when we're comparing something along the lines of a book, or an inventory, or an item. We as the programmers need to define how to compare those 2 objects, or any 2 objects of that type. In C++, we overload the logical equivalence operator. In Java, we define an equals function. In Python, we define a dunder equals function. Dunder being the double underscore you see there. Double underscore EQ, double underscore. Hash code's a funny one, but we'll ignore that one for now. But it more or less, it's analogous to our C++ less than operator. Note how I said analogous and not equivalent. The stream insertion operator in C++. If we have defined our own type, we want to be able to output it. In Java, if we have defined our own type, we want to be able to output it. So we define a function that generates a string, and then we output that string. Python, dunder str. Generate a string so we can then output it. And if we have a class, a data type we have defined that is itself a container, a collection of other pieces of data, we want to be able to iterate through that data. In C++, we provide an iterator, and our class provides begin and end functions. In Java, we provide an iterator, and our class provides a dot lowercase I iterator function. In Python, we define a dunder iterate function. That is, once again, double underscore ITER. So I want you to keep that in mind. Now, I'm going to go ahead and jump back to our tic-tac-toe discussion now, which is what you see on my editor here. Now, I do want to pick up with one quick note. So let's go ahead and compile this. Now, when we finished up the last discussion, I was talking about the dash wall, meaning dash WALL compilation flag. And we had a few warnings, and I've eliminated a few of them between our discussions. One of them, the main one being all the errors that dealt with W reorder, I've eliminated. I'm going to come back to that one in a moment. Now, we discussed last time that is generics not being used here, so that's not necessarily an issue. But we will see it is used elsewhere in our test later on, so that's not an issue. And we argued away the comparison between signed and unsigned integer expressions, meaning we know that I can be positive, negative, or 0, and we know that by virtue of how we're writing our code, we will never decrement I. I will either be 0 or higher, but it will never be negative. So we can get away and ignore that warning. Now I want to talk about what I've changed specifically in game.cpp. Now, you should remember the W reorder compilation errors from our previous discussion. If not, go back and take a look at the last 10-15 minutes or so, the discussion before this one. Now, I'm going to go ahead and look for something specific. This guy right here. So let's go ahead and zoom in just a little bit more, just to make this a little bit larger. This was the issue here. You probably have noticed that if you look here and you look here, I have changed the order of the entries in my initializer list. I'm initializing the board first, then I'm initializing the referee, then I'm initializing players 1 and 2, then I'm initializing the winner pointer, then I'm initializing the number of moves made. Now, this is what our W reorder warning was flagging last time. These were not in the correct order. Now, I did have to do a little bit of review reading just to recognize what that meant. And the major thing here, the major note about initializer lists that I did not realize or that I had forgotten, I cannot remember, well, technically both. So let's say both. I had forgotten and I did not remember, or I did not realize, right? I think all those things overlap. The initializer list is not executed in the order we write the entries. The initializer list is initialized in the order those data members were declared. So if I go back to game.h and I look and I scroll down a little bit here, you'll note that I have reordered my initializer list so that it initializes all of these in this order. Meaning board is the first piece of private member data I declared. I need to define it first. Referee is the second piece of private member data. I need to initialize it second. Player 1 and player 2, third and fourth. Winner, fifth. Number of moves made, sixth. But this is where that ordering comes from. If I go back to game.h and I go to I guess I should probably just go with board and then the opening paren. There we go. We can see that the ordering here is maintained. I initialize the board, then the referee, then players 1 and 2, then the winner pointer, then the number of moves made. Now last time, so that's really the note I wanted to make there. And now I want to switch gears a little bit. We've spoken about how this is implemented and we've gone through the implementation of all of these classes. The focus of this discussion is going to be on testing. Now, this looks very complicated. And at first glance, maybe it is. But it really isn't. So this guy right here is what's known as a preprocessor directive, a define macro. Now, anywhere you see me write bodge assert and then some expression, it's going to expand out to this. So I'm going to go ahead and just copy this so you can see what I mean. Now, when I wrote this, I wanted a way to write a unit testing framework in C++ without having to go through the hassle of setting up something more robust. For example, the Google test framework, the Boost unit testing framework, all of that. I just wanted something quick and something that mirrored how I used to write my quick and dirty tests, and maybe how I still do in some cases. So let's go ahead and grab this and just see what happens here. Let's go ahead and grab that guy and paste him above so we have our frame of reference. So what I'm doing here is I'm creating a brand new game board. And what I've said here is that's the string that represents the board in its initial state. The numbers 1, 2, and 3, new line, 4, 5, and 6, new line, 7, 8, and 9, and then a trailing new line. So what I want to do is when I construct the game board, I want to check and make sure that when I print it, I get what I expect back. So to help with that, I need to be able to use my stream insertion operator for output, but I need it to generate a string for me. So I've defined a custom toString function, toStr. And what that's going to do is that's going to take any arbitrary type that I pass into it. It's a templated function. It's going to create an output string stream, which allows me to take the stream insertion operator, and instead of writing to the screen, I can write it into a string. So whatever the thing, whatever the object is I want to write, it's going to write into that stream, that output string stream. And then as soon as I'm done, I can take that output string stream and get whatever's in it in the form of a string. A very quick and dirty trick, and a very old trick now, but a very elegant one nonetheless. So now that we have that, let's go ahead and grab all of this. And let's start updating this to see what I'm actually writing here. So this is what I've written, essentially. I expect these to be the same, meaning I expect my initial game board to match that expected initial exactly. If it doesn't, I expect an error. Now you notice that I've taken the expression, wrapped it in parentheses, and then I've negated it. I'm saying, look, if this check fails, if this evaluates the false, I have a problem. So I'm going to output which test function failed. In this case, test board but poorly. The line number, in this case, is going to be line 3. And then the actual condition I wrote. So in this case, yank. In this case, I'm going to output as a string. So let's make sure I get this right on the first try. And I did. So what I'm basically doing is this. Well, not basically, exactly what I'm doing is this. And then, of course, that. So I've just expanded out that preprocessor directive. So I'm saying here, look. When I write this, whatever I've written on line 70 by the preprocessor is going to expand out to this. It's going to take that Boolean expression, meaning that expression that evaluates a true or false, dump it into a conditional block in this form, and if that test fails, then the block will execute. If the test runs without issue, I get no output because it was successful. But this is what I'm doing here. It's a quick and dirty unit test framework. Now, if you think about this, I would be very surprised if you have not written something like this before in the past. Meaning, you wrote some code, you wrote a test driver, you wrote a conditional block, and then you output some stuff and examined it. I've sort of taken that and I've cleaned it up a little bit. Meaning I've taken where I can reuse it without having to write this conditional block every time. I've basically taken the test logic I would normally write, and I've applied the dry principle to it. I did not repeat myself. I do not want to repeat myself. Dry means do not repeat yourself. So that's all this Bodge assert does. That anytime you see a Bodge assert, it's expanding out to a conditional block in this form. And you may have seen this in a CS330 assignment if I gave you the unit test. So let's go ahead and clean this up and just reopen the file. So that's what's happening there. Now, I don't want to get too much into what's up here, mainly because it is support code to run all the tests. But what it really boils down to is, in C++, we have spoken about pointers. We've discussed pointers in previous classes. There's also something called a function pointer, a pointer to a function. It is possible to define a variable that allows us to reference a function and call that function and change what we're doing. It's very useful when you're doing numerical calculations. But C++, 11, 14, and such provide a wrapper for that to make it, well, more robust. And that is the standard function. So this is a C++ 11 way of getting a function pointer. Now, looks scary at first, it's really not. So I'm creating a function pointer, standard function, and I'm creating a pointer for a function that takes no arguments and returns a Boolean value. That's all that means. And I'm giving it an alias. The alias is unit test function. So anywhere I write unit test function, that will expand out to standard function equals bool parens, so on. Then below that, I've defined a unit test pair, which is your standard pair, which we've discussed before, where the first part of that pair is a unit test function pointer, and the second thing is a string, a descriptive string. And then I have a run test function down here, and all that does is take a unit test function pointer and a description. It runs the test, outputs passed if the test passed, outputs failed if the test failed, the description for that test, and then an end-of-line character. Now, you may be wondering why I didn't just say expand that out automatically, meaning why am I typing the function name twice, once to create the function pointer and once for the description? Well, I thought when I was writing this, you know what? Right now, I want to output the function name if it fails. But in the future, I might want to give it a more descriptive name, meaning first board test or something a little bit more descriptive. So I wanted to leave myself that flexibility later on. And this is the main function down here. What I do is I create an array of unit test pair, meaning an array of pointers, an array of function pointers. I'm using something called an initialization list, which will handle all the heavy lifting and constructor stuff for me. And right here you can see I only have one test, an array of one entry, which isn't all that elegant. And then I have a range-based for loop below that will go through that array and then run the test, passing in the pointer to the test function and then the description I want to use for it. And that's really just the test driver harness, the test harness, if you will. It is not the actual test, which we have right here. So now when I look at this, it should be a little bit more straightforward what I'm trying to do and what my intentions are, what my test is actually doing. Syntax-wise, and the syntax and the mechanics, that's another story. But the notion here is, I am used to testing my code. I am used to looking at the output and saying, is that correct? I don't want to have to look at output and say, is that correct? I want a framework that will do that for me. I want to be able to write a test, make sure the test is correct, and then see a test report. That test passed. You're good to go. I want to be able to automate it. And that's what this BODGE unit testing framework, as I've called it, allows me to do. So this function is called test board but poorly. Now, there's a reason I've said I am testing the board, but I am doing it poorly. And I'll come back to that in a moment. So we've already covered the first step. To test the board, I have to create a board object. And that's the first step you see up there on this line right here. I've defined a couple variables, what I expect the board to be initially and what I expect the board to be once I filled it up. I've written my first test, does the board output what I expect when it's empty? And my second test, well, I've just created the board, it definitely should not be full. And that's what that second test will check. Then I'm going to go ahead and go through my entire board using the setCell function. And I'm going to check to see that if I set everything to X, if I fill up the board, do I get what I expect? And does the board report itself as being full? If these tests pass and I make it to line 79 here, I will consider the test as having passed. Now, I've called this test board but poorly. First and foremost, there's one test function. Secondly, I'm testing the constructor and setCell mutator simultaneously. So if there's a flaw in my constructor, it's going to be difficult to tell whether it's in the constructor or in setCell. If there's a flaw in one of my accessors, toString or isFull, it's going to be difficult to tell. So this test doesn't really help me all that much. I need to refactor it and I need to think of a few things. So, when I'm writing tests, there's a methodology I need to follow. And I'm going to come back to that in a little bit. I want to cover another test real quick. I want to look at test player. But the methodology here is a step in the right direction. It is not the methodology we want to follow. It is not robust. It is not complete. But let's go ahead and take a look at test player. Now, this is the unit test for the player. It follows the same basic framework, same basic setup. I have the same toString helper function. I should really refactor this. And I have a function called test player default constructor. Fine. I create a new player named Tom. Fine. When I print the player, do I get Tom back? Is the name set correctly? And I think it should be a little bit more obvious why this test is bad. Or this test suite overall is bad. Well, does set name work? Does get name work? Does set symbol work? Does get symbol work? Does comparing two players work? I want to make sure that the entire interface, my entire implementation is correct. And all this does, this function right here, is check my constructor and check my display function. I've ignored the rest. And that's the point of this comment at the bottom here. Where are the rest of my tests? If I'm lucky, I might get an F on this. What's worse than an F? Well, getting an email saying, hey, what's going on? How come you didn't write your tests more completely? That's worse than an F in my opinion. But this is a very, very poor test. This is a good initial step. It's a step in the right direction, but it is woefully incomplete. Now, I want to use a more robust testing framework. Now, the ones for C++, the Boost Unit Testing Framework, the Google Test Framework, Dr. Zile's Test Framework, they require more setup than I would care to have here. So what I'm going to do here for this discussion is I'm going to say, we've covered our C++. Now what I want to do is switch gears. I want a language with a test framework that's more or less built into the language, and a test framework that is considered robust and is actually used. So we're going to switch gears for example 4, and we are going to switch into a language called Java. Now, Java is a simple language, I would say. Now, what do I mean by simple? Well, it is very, very similar to C++. Now, when we start going through this code, there will be a few subtle differences, but nothing we cannot address as we're going through it, meaning about 90% of what you need to know to understand this Java code, you already do because of what you understand from C++. So let's go ahead and open this. Now, for this Java code, I am going to be using a build system called Gradle. Now, this is the Gradle build script. It's sort of like our makefile for C++ and such. If you are interested in that, if you're interested in Gradle build files, I have provided the CS350 reviews to you, and you can take a look at those. But we are not going to spend any great deal of time on Gradle here. We are simply going to rely on some makefile stuff. Now, it looks like I still have a makefile I shouldn't, so we're going to ignore that and pretend it doesn't exist. Now, when you set up a project with Gradle, you separate your code into two directories. A main Java directory, which is all of your production code, and then a test Java code, which contains all of your unit tests. Now, let's go ahead and jump into play tic-tac-toe. Now, one of the major differences between C++ and Java is everything in Java must be wrapped in a class, even the main function. So right here, you see a function named play tic-tac-toe. Excuse me, a class named play tic-tac-toe with the main function contained therein. Now, the signature for the main function is a little bit different in Java. Strings are named properly with a capital S, and they're imported automatically. Now, at the very top here, we see an import java.io.io exception. Now, this is an IO exception, and IO stands for input-output. So, an error reading from the keyboard, things like that. But the import in Java is equivalent to the C++ include, with the caveat being we are generally more specific with Java imports, meaning we're importing the specific class we want. We're not importing everything all at once. So if I look at the code here, this looks very similar, if not identical, to our C++ code. Now, the caveat here is you'll notice that player Tom equals new player Thomas and so on. And now if I look at this, this does start looking a little bit interesting. If this were C++ code, I would see pointers, asterisks, like this. Now in Java, anytime I have an object variable, it behaves similar to how it behaves almost identically to how I would expect a C++ pointer to an object to behave. So anytime you're working with an object variable in Java, the same basic notions of C++ pointers to objects apply. You're going to use new, you're going to allocate it explicitly. So player Tom equals new player, and then whatever I want to pass into that constructor. And the same thing for J. Once again, this example, Tom refers to me, Thomas, I'm using myself as an example, and J refers to Professor Morris. I'm going to construct a new game with those two players, Tom and J. And we're going to keep playing one round. We're going to keep playing one round until the game is over. So while the game is not over, we're going to keep playing. And then once the game is over, we're going to print the board one time. And if the game ended with a win, we are going to congratulate the winner. Now, I don't know about you, but I would very much like to see the game being played. So let's go ahead and demonstrate how to compile this. So the command I'm going to use is /Gradle W no daemon. This is because I don't want a background process continuously running. And it does look like I haven't run this version of Gradle before, so this is going to take a moment to download. Now, this is the beauty of the Gradle wrapper. You do not need to have Gradle installed on your system to run this. You just have to have the JDK for compiling Java, the Java compiler, and the Java runtime environment. If you have both of those, you run the Gradle wrapper and the rest is done for you. Now, this is going to take a moment to run, which is not quite what I expected. I thought I had run this already. So let's take a step back and not waste time. Let's take another look at my rightmost monitor here. Now, if we look at this, our default constructor translates from C++ to Java 1-to-1. Our copy constructor translates to Java 1-to-1. Our accessors and mutators translate directly 1-to-1. Logical equivalence translates to a function with a different name. Double equals in C++, equals in Java. If we want to output in C++, we write directly to the output stream. If we want to output in Java, we generate a string and then output that string. So it looks like it has completed execution, so let's resume that. So good, that handled all the Gradle bootstrapping stuff, and now I have Gradle set up. So next time I run it, I can just do, and I can never remember what the command I wanted, so I'm going to do Gradle W tasks. It's going to run Gradle, and it's going to tell me every option I can run here. Now, if you have Eclipse set up, you can run Gradle W Eclipse. It will create an Eclipse project, and you can then go ahead, compile, and run it. Now, what I would like to do here is run Gradle W test. So let's go ahead and run our tests here. Now, this is a very nice thing about Gradle. It's going to figure out all of the dependencies for me. So if I need to run tests, it's going to compile my base code, my production code, and then run my tests. And it will give me a report on which test passed and which ones failed. Now, I also want to run, I want a test report here. So I'm going to run this again. And I'm going to generate a test report. And now, while that is running, I'm going to go ahead and navigate to this example directory and bring up the report. So when you write tests, there are two things we want to look at. Is our code as a whole fully exercised? Meaning, after I run all of my tests, have I gone through every branch of my code? And secondly, is each of my tests complete? Is each of my tests on its own thorough within that test suite? Now, this is example 4, and I do want this reports directory right here. Right there. So I'm going to go ahead and go to Jacoco right here, right now. So let us see test report, and that is what I want. So let's go ahead and bust that window out and dump it in here. So everything's in the default package. We'll get to what that means in a moment. This gives me a report of all of my tests, meaning my test coverage specifically in this case. Red means things I did not test. Missed instructions, missed statements. I have a lot of red. These tests are really bad. They're woefully incomplete. So I think player is probably a good place to start, and then board would be a second place. Now if I look, I tested a few functions. I've tested toString. I've tested a constant. I've tested both my constructors. And I've tested getName. but I haven't tested the rest here. So let's go and just pick one arbitrarily. So this is the report, and any line highlighted in green is one that was executed by one of my tests. Any line highlighted in red is one I missed entirely. And as you can see, lots of red. Lots and lots of red. If I go to board, much the same thing. Any line in red is one I didn't execute. Any line in green is one that was. And I did slightly better with board, I would say, but not that much better. Not that much better at all. Now, there are a few other reports I want to bring up just for sake of completeness. One is called Find Bugs. And this will flag any lines of code that are known to be potential bugs. And it will give me some warnings about things. Now, this is much like the dash wall flag in C++, but far more complete, far more... well, I would say far more precise, far more overarching, far more comprehensive. Now, this will give me some more warnings. It's another tool called PMD. And then there is another tool called Check Style. And this will flag any sort of poor style things I've done here. For example, if I have trailing spaces, missing Java doc comments, anything called a magic number, meaning if I'm comparing to 7, why is it 7 and not a constant? I'm missing some white space and all of that. And I'm using an inline conditional, meaning the ternary operator, all of that. So it will flag quite a bit here. But those are discussions for another time, things we discussed in 350. But the point is, there are tools that will examine our code. And right now we are interested in two. Jacoco for test coverage, and more importantly, JUnit for actually running our tests and getting our test reports. Now, for sake of completeness, let's actually look at the report we can get for JUnit. Now, if I look at that, that's going to be in this reports test directory. And this is my test report here. And it's going to tell me what test passed, what test failed. I can look at which classes and all of that. And yes, my success rate is 100. But as we just saw, my tests are woefully incomplete. So I'm not surprised my tests passed. All right, I probably checked the easy things, forgot about the more difficult things. And for all I know, my implementation is complete garbage. And the only functions that work are, well, for player, the constructors, and get, name, and toString. For all I know, these functions right here are completely wrong. I never tested them, so how can I know? And that's one of the major things in test-driven development. One of the major rules in test-driven development is if I do not have a test for it, it does not exist. If I do not have a test for it, I have not written or implemented the function. So any function I have must be executed by one of my unit tests, by at least one. So now, let's go ahead and take a step back and actually run the main code. So assuming I set this up correctly and I added a run target, it looks like I didn't add a run target. Fine. That's okay. I'll do it a different way. I'll create my jar file and run it manually. A lot of times I'll add a target so I can just run it directly, but I forgot to do that here. So now I'm going to run it manually. And that's going to be java-jar. And my jar file is here. Build/lib. And play tic-tac-toe.jar. So the command to run the main code is java-jar. My jar file is in the build directory, so build/libs/the jar file name. And now we can see it is actually running. So let's zoom in just a hair more. So what I see here is Thomas, enter your desired move. Now I'm going to select the center cell. Now Morris is going to go and he's going to grab the top left. I'm going to go and I'm going to grab the bottom left. Morris is going to counter in the top right. Then I would probably go for a spot that gives me a chance of beating Morris. So I'm going to block him from getting 3 in a row. Then Morris is going to block me from getting 3 in a row. Then 4. Then 6. And then 9. And nobody won. as we can see there. So the game exited, nobody won, no output. Hooray. Now, that tells me that the game ends in a stalemate correctly, but what it doesn't tell me is, does it detect 3 in a row correctly and all of that? And I would very much like to not have to run my code step by step, repeatedly, every time I make a change. I would like to be able to automate that testing. And that's where my test classes come into play here. So I'm going to zoom out a little bit here in Vim just so everything's about the level I expect it to be. Now the big issue here is not all of my classes are tested. You can see I have 4 classes: board, game, player, and play tic-tac-toe.java. Now, one thing you're going to see here is play tic-tac-toe.java is just a wrapper for my main function. So that on its own doesn't need a test. We can ignore that one. That leaves us with 3 classes, but really 4. Now, why do I have 4 classes? Well, if I look at game, right here, I have the referee. The referee is an inner class within game. If I have a class, I must have a JUnit test suite for that class, or in general, a test suite for that class. Right now, I only have 2. I have a test for board and a test for player. I don't have a test for game, and I don't have a test for referee. So let's take a look at these tests and see what we're getting here. So before we do that, let's go ahead and do let's reopen that and close that. So our game has referee as a private inner class. So now if I take a look at my tests for Java here, you can see I have far more imports this time, and I am going to be using 2 libraries: the JUnit library, the JUnit testing framework, and Hamcrest to give us some nice readable matchers. So as opposed to writing assert true or assert false, I can also do assert that and have more readable assertions. Now, anytime I write a unit test, there are 2 things I'm checking. There are 2 questions I need to answer in each unit test within my unit test suite. Does this piece of code perform the operations it was designed to perform? That's the one nobody argues with. The second one, everybody always forgets. Does this piece of code do something it was not designed to perform? Meaning, if I change the name, if I have a function called setName, it should only change the name. I would be very surprised if it also changed the symbol, for example. Now, this is more or less a copy and paste of my previous test from the C++ BODG unit testing framework. Line-to-line, one-to-one mapping. I'm constructing a brand new board for my test. I'm defining a string that says, when I first create the board, this is what I expect. And once the board is full, this is what I expect. Now, I'm using the assert that function. So I'm taking my board and using the board's built-in toString function. And then I'm taking that toString function, which gives me a string that representing that board, and I'm comparing it to what I expect. Is the result of this board toString function call equal to that expected initial string? Are they equal? If they are, I go past this line, my test continues. If this assertion fails, my test halts, I get that in my report, and the rest is downhill from there. At this point, the board should not be full. So assert false. The board should not be full. Board.isFull should return false. So assert that I do in fact get false back from that. And then go down a little bit more. Board.setCell. I'm going to fill up the game board. I'm going to fill it up with X's. And then when I rerun the test, I should see that I get the expected final string and that the board is in fact full. Assert that the board is full function call yields is full. But if we look at this test has a one-to-one mapping, meaning each of these lines here has a one-to-one correspondence to the C++ version. This is how similar C++ and Java can be, and how similar they are in a more general sense, with a few caveats, of course. But notice I don't have any of these test harness functions I wrote because the Java JUnit test framework handles all that for me. I just have to write my test functions. Now, this right here is what's known as a decorator at test. Now, when I'm writing JUnit tests, any function I have that represents a test, I need to, on the line before, denote that it is a test with this decorator, at test. Now, when I have a test suite, there are a few things I can do beforehand. At fixed method order, all this is going to do is make sure that when I have a set of test functions in here, they're going to run in order based on their names. Not necessary, but it makes my life as a programmer easier. Then if we look at test player, we're also going to see a one-to-one mapping, a one-to-one correspondence. And if we look, there is once again a one-to-one correspondence to the C++ version. I am going to construct a brand new player named Tom. Now, I am going to assert that when I call Tom that .toString here, and I'm going to use a standard JUnit assert equals here. I'm not going to be fancy with the Hamcrest matchers. I'm going to say that, look, when I call Tom.toString, I should get capital T Tom back. That literal string right there is what I expect to get back. Tom.toString should give me that result. So, that's what I expect. So, assert equals line 28 is going to run. If Tom.toString returns a string that matches Tom exactly, that assertion passes, and we continue running tests. Now, if I want to get fancy, I can get something like this. Assert that the result I get back is equal to Tom. So both of these tests are equal. Assert equals and assert that. These two tests right here are equivalent. They check the same thing. One is the standard vanilla assert equals. Another one is the Hamcrest assert that, which reads more like a sentence. Assert that Tom.toString is equal to Tom. It reads more naturally. So our test becomes more self-documenting, I would say. Now, you're probably asking yourselves, well, we're talking about these tests, we're talking about Java code, how come we haven't discussed the classes? Well, there are a few reasons for that. Main thing I wanted to do here is emphasize how similar the tests are and emphasize how similar the C++ and Java syntaxes are, and a few of the low-hanging fruits, meaning a few of the things that are ever so subtly different, meaning if I'm working with an object in Java, it's a reference to that object. Now, I'm making fun of the term reference because functionally at the end of the day, it is really a pointer by a different name. And if you invent a programming language, you can name things whatever you want. But I'm going to make that joke about the people who created Java calling these types of variables references when they're really pointers. Well, fancy pointers, but pointers nonetheless. So anytime you hear me use the term reference in Java, just think of it behaving more like a C++ pointer. It's basically a Java pointer at the end of the day. So now let's start going through this code. Now we've looked at one of our classes so far, play tic-tac-toe, which is really just a wrapper for our main function. Fine. So let's look at something a little bit more complete. Our player class. Now, one of the big things we're going to notice very quickly is that in Java, there's no notion of header and CPP files. There's no notion of declarations and definitions being separate. Those of you who come from backgrounds in languages like Java or Python or the dark side, C# and such, will be right at home. Write everything in one place, and there it is. Yes, C# is the dark side. Java, yes. I'm going to say Java and Python are better, but personal preference. Unlike Vim versus Emacs, where Vim is the only correct choice. So looking at this, you can see I've taken my documentation from the C++ code and left it mostly unchanged. And you can see I've translated everything one-to-one. Now, there are a few changes we might need to make this idiomatic Java, meaning Java written in the Java style. But for now, I'm going to leave it as a more or less direct translation from C++. The notion of a class, that translates one-to-one. The notion of a static constant, that translates one-to-one, even if the syntax is a little bit different. This is a constant. Now, in this context, right here on this line, in this context right here on line 14, final is behaving the same way as const does in C++. But that does not hold in general. Final in Java is far more context specific. But line 14 is giving me a static constant. Prompt message, same as the C++ version. I still have my two private data members. And now one thing you're going to note is in Java, I don't do public colon or private colon. I list public or private before each entry, or rely on whatever the default is. So you're going to see public and private listed everywhere. Then I have my reference Cylon. Once again, another constant. A non-descript player, I see generic. Then we go down a little bit further, and we see the isGeneric function. And it's almost identical to the C++ version, except in C++ it was possible Cylon double equals reference Cylon. Here it's going to be possible Cylon dot equals player dot reference Cylon. Same thing. Slightly different syntax, but there's a one-to-one mapping. There is no notion of an initializer list in Java, at least at the time of writing. So I'm just going to do a plain vanilla assignment. I need to set the name attribute to ICGeneric. Now you will note that I am violating the rule of constructors, meaning every constructor must initialize every attribute, and it's one I've been violating all along. I'll leave that alone for now. We'll let that come up in one of our tests later. But when I write my test, that should be flagged immediately. When I'm writing a unit test to see if the constructor is working correctly, and I try to check the symbol, I'm going to recognize really quickly that I never initialized the symbol. So hopefully my unit tests pick that up later. Meaning the revised versions of what we've discussed. My non-default constructor allow me to create a player with a name I desire. Get name and set name, well, those translate almost directly from C++. These translate directly from C++. Get name and set name. Return the name, get the name. So the notions of getters and setters translate one-to-one. Now, it would help if I were in the right window, wouldn't it? So I'm going to skip next move and come back to that one. Is human player and is computer. These are simply return true and return false as they were in the C++ version. And that brings us to another difference between C++ and Java. Boolean is spelled out in Java. And the notion of a const function doesn't really exist in Java. There is a similar notion with final functions, but it is ever so slightly different. Well, it is fundamentally different. But the notion of a function being const in Java doesn't really exist. And I'm going to do some hand waving there. Because there are final functions in Java, but they're different fundamentally. Then I have get symbol and set symbol. Once again, one-to-one mapping to the C++ version. And then toString. In the C++ version, we wrote our name to our output stream. In Java, we're just returning the name. And now we can start seeing the emergence of our Java class checklist. In C++, if we want, whenever we write a class, we have the stream insertion operator. In Java, we have the toString operator. In C++, we have the double equals for equivalence. In Java, we have the equals function for equivalence. In C++, we have less than. In Java, we have hash code. They are not equivalent, but their use is expected for similar reasons. So they are analogous. So hash code is just an integer that represents the state of our object. Now, if our equivalence check is based on name, meaning if our equivalence is keyed based on player name, our hash code must be as well. So if we check for equivalence based on name, we generate the hash code based on name. And right here, I'm just going to say, well, the built-in string class, that has a hash code. I'm just going to forward that through. So whatever the hash code of my name is, whatever the hash code of that string is, that's the hash code that represents this player. Then equals, well, if we look, there's this little notion here. And you will note this is ever so slightly different. Equals doesn't take another player object. Equals takes this capital O object. Now, in Java, there is this object-based class from which all classes inherit, meaning player extends this object-based class. So to override equals, I must accept that. So the first check I do is I check to see, is the right-hand side an instance of the player class? If I pass in a string, if I'm trying to see if a string is equal to a player, that's not defined, so I'm going to go ahead and just say, nope, they are not equivalent because they are different classes. And then after we get past that, this line match, and then I have to do my typecast to take the right-hand side and turn it into a player. And then this check is equivalent to our C++ version. Take this name, take the left-hand player's name, and compare it to that right-hand side player's name. If the names are equal, it's the same player. And notice right here, I'm not using the player's equals function, name.equals. I'm using the string equals function. And that's our player class. Now if we go up, we get down into next move. Now I'm using the Java scanner, and I'm going to come back to that in a later example. But what I'm using it to do here is I'm using it to read from standard in. Now there are some very strong opinions on the use of the Java scanner, but I'll leave those discussions for a later example once again. We see a line similar to our C++ version. The player's choice as an integer, the position on the board. I'm going to output to the screen that prompt message, Thomas, enter your desired move. And then I'm going to use the scanner to read the next integer that player inputs. So if the player enters anything other than an integer, I'll have an exception that bubbles up, everything will halt, and then things won't go low. But once again, we're going to assume legal input all the time. So if I were to, for example, enter 5 to select the center of the board, I would grab 5, that would be stored in choice, and then I would then return that result. But once again, the same issues for next move from the C++ version translate over here. I'm still stuck to standard input. I cannot test next move, at least with the unit test as I intended. So that's our player class. If we look at our game class, it's very much the same. I have the referee inner class and all of that. I have all of my checks, lots of things. Very similar to the C++ version. Very similar, very similar. Now, I did scroll through that very quickly, and I am going to come back to it, so don't worry about that. But if I look, I still have my board, private data member within game. I still have the referee. I still have players 1 and 2. I still have a winner, and I still have number of moves made. Now, you will note that I don't have any pointers here. They're all players, because these are going to behave very, very similar in a very similar fashion to C++ pointers, meaning these are references to objects, not the objects themselves. Then the number of moves made, which I never use. Now, I discussed a little bit earlier in my previous C++ discussion that in Java, to suppress the use of a constructor, I must make it private, and I've done that here. Then I have my public constructor, set my 2 players, set up the game board. So set my 2 players to what I passed in, create a brand new game board, create a new referee with direct access to that game board, and set player 1's symbol to X and player 2's symbol to O. Then play 1 round. If we look at this logic, it is identical to the C++ version. Start the game. Start the round. If the board is full, the round ends immediately. Then output the board. Let player 1 go. Then check to see, is the board full? If it is, output the board and say the round is over. Then check to see if player 1 has won. If player 1 did in fact win, say that the winner is player 1, return true. We'll set the winner to player 1. Then, if player 1 didn't win, let player 2 go, output the board, check to see if player 2 won. If player 2 did in fact win, set the winner to player 2, return true. And if I reach that very last line, I reach the end of the round and nobody has won yet. Get player 1 and get player 2, identical to the C++ version. Get winner, near identical to the C++ version. Get loser, similar to the C++ version, except now I'm returning null. Because, yes, in Java, it's lowercase null. Now, in Java, these player objects behave like you would expect pointers in C++ to behave, which means they can store null. And that's what I'm going to leverage here. If my game ended with a stalemate, there is no winner, so I'm going to say the winner is null. There can't be a winner, as opposed to the reference Cylon, as I did in the C++ version. Then, winner.equals player 1. So if the game did not end with a stalemate, I know for a fact there was a winner. So, if the winner is equal to player 1, so if player 1 is the winner, that means player 2 is the loser. And then if I reach this last line down here, line 36, I know that if player 2 won, player 1 has to be the winner. Excuse me. I know that player 2 won, player 1 has to be the loser. And I know that if I reach this line, this evaluated to false, and that I end up down here implicitly. So this is my implicit else. Ended with win. Well, it's a far easier check in this version. If the game ended with a win, winner is not equal to null, meaning I have a winner. It's either player 1 or player 2. If the game ended with a stalemate, it translates directly from the C++ version. If the game ended with a stalemate, the board is both full and there was no winner. So winner is null. If the game is over, well, it ended with either a win or with a stalemate. If the game is not over, well, I'm just checking. Is the game over? Negate the result. Get direct access to the original board, or the board within the game. And then round turn, once again, a direct translation of the C++ version. Have player 1 go. So get player 1's move, get player 1's symbol. Have the referee check and see, is the selected cell empty? If the selected cell is in fact empty, well, it's a legal move, let the player go. But if the selected cell is not empty, that means the move is not valid. So I have to reprompt that player until he or she selects a cell on the board that is not empty. And that's what this loop handles, just like in the C++ version. Now, once the player has made a legal selection, selected a legal move, meaning selected an empty cell, I'm going to update the board. And then, once I reach this point, there was no issue, so return true. Now, this function sort of contradicts itself because it's handling that move validation where my original design didn't call for that. And this is one of the reasons we want our design defined up front. We don't want functions to arise like this where it always returns true and I've changed my design halfway through. I want to have that design finalized before I write line 1 of implementation. Okay. So, referee is more or less the same as the C++ version, but it is an inner class, and we're starting to see the point where making this an inner class was probably a mistake. It's far too complex for an inner class. I'm not using it for data storage. I'm going to end up making it its own public class in its own right, or at least a first level class within the package. I can always make it private within the package. But I'm still going to have a reference to the board. Now, note the notion of final here. Now, this is a different notion from final before. This is, once I have set the board reference, I don't want to change it, meaning I will not be able to change the reference to the board once I set it. So right here, this is my default constructor for referee, which I've hidden. And if I ever somehow find a way to use it, my code won't work because null isn't a board. Right? It's the lack of a board. But if I create a referee properly, I set the reference to whatever I pass it. And then I have direct access to that board in any function. I'm sharing that board between the game and the referee. So final in this context does not prevent changes to the board. It prevents me from changing the referee to reference a different board. Check for a win. It's the same as the C++ version. First, I'm going to check for a horizontal win, then for a vertical win, then for a diagonal win. But the logic translates 1-to-1, at least for that function. Selected cell is empty. Well, I don't particularly like the indentation here. It hits that 80 character limit, but I'm going to go ahead and fix that. So this hits the 80 character limit, so let's go ahead and fix it by doing our line break as is convention. And let's enter a lowercase w. Much better. So a cell is empty if a player has not selected it yet. So if the cell does not contain neither an X nor an O, I'm going to consider it empty. Then I'm going to go down a little bit further. Check for horizontal win. We see it translates almost directly from the C++ version, except at the time of writing, Java does not have a built-in pair class, so I had to define my own. But it operates the same way. And you can see I made it mirror the C++ one. So I still have a board get 3 cells function. And I'm going to check and see. Do all 3 match? And the rest of the logic is identical to the C++ version. Then I go down a little bit further. Check for vertical win. Once again, one-to-one mapping to the C++ version. Diagonal, once again, one-to-one mapping to the C++ version. Go down to all three match. A one-to-one mapping to the C++ version with a standard loop. Now I have an array called triple. So it's going to be an array of 3 board pairs. Yes, I can pass in an array like this in Java as an argument. This is the syntax. I'm passing in an array. So there we go. I know that it should be 3, but I'm going to go ahead and use .length just to emphasize that. In Java, arrays have this length attribute. So I'm going to grab the first value from the first pair in that array. So the first character. And I'm going to check to see. If I look at all 3 of these cells, are they all X's or are they all O's? It doesn't matter which one as long as they are all the same. If, when I write this, I have 3 matches, if all 3 of these cells contain the same character, they all match. Same logic as the C++ version. Now, just like in the C++ version, I have a get player name from symbol or player number from symbol. So if I pass in X, that's player 1. If I pass in O, that's player 2. But this is more or less a one-to-one mapping to the C++ version. And now that just leaves, let's go ahead and write that and compile this. Let's go ahead and jar test. So while this is compiling, I want to think a little bit. That leaves just the board class. So we can see both of my tests still pass, so that one change I made doesn't make them fail, even though my tests are woefully incomplete. So that this report is basically meaningless. But so far, the Java code has been near identical to our C++ implementation. Now, part of that is due to me setting it up that way. The other part of that is just how similar C++ and Java can be. Now, I have my board class, and I had to define my own pair class within that. And we can see it's exactly what I expect. The first entry is an integer, the second is a character, and it mirrors, it's basically an implementation of the C++ standard pair for an integer char pair. Then my board has an array, the board. It's still going to be a one-dimensional array, just like in the C++ version. My constructor, if I look, same as the C++ version. Create a new array of size 9. Had to add that for the Java version. I had to allocate the array. But same trick, except Java doesn't do the implicit casts like C++ does. Excuse me. And in Java, it's considered better form to explicitly cast, so that's what I've done. So take the O character, convert it to an integer, add the appropriate offset to it, and turn it back into a character. So first cell will be numbered 1, fifth cell will be numbered 5, so on and so forth. Same as the C++ logic. Now, this isn't proper JavaDocs syntax because JavaDocs doesn't have a precondition, but I just copied and pasted my Doxygen documentation, so we'll forgive that for now. Get cell is the same as the C++ version. Set cell, same as the C++ version. Get 3 cells, same as the C++ version. Is full, same as the C++ version, except the isDigit function in C++ is part of the standard namespace. The isDigit function in Java is part of the character wrapper class. But the logic is the same. And then my logic for the toString function is the same as my C++ display function, except that I'm using a string builder because string concatenation in Java is expensive. In Java, strings are immutable. So anytime I'm building a string, I'm either going to use a string builder or a string buffer. So instead of doing one string plus another, I'm going to do string builder dot append each time. The logic is the same, but anywhere I had a plus in the C++ version, it's now string builder dot append. So build dot append the current board character and then the pipe character. And then in the very last cell, append the last cell and a new line. And then once I am done, once I've executed that loop and I've built the entire string representing that board, take my string builder and get the resulting string and return that. So now I'm done with the board. The logic is the same. And what we've seen here is, based on our knowledge of the C++ version, we can go through the Java version very quickly because the logic is identical in this implementation. We can write Java code based on our knowledge of C++ with a few subtle changes. Now, those of you familiar with Java will recognize one glaring flaw. Everything here is in what's called the default package, which is considered extremely poor form in Java. So, let's clean this up. So I'm going to go ahead and jump into example 5. Now this is example 5. Lots of things. So, and I want to do just the source directory. And I want to pipe that into less. So ls-l is the listing and r is recursive, so it will go through each of the directories. Now we can see there are multiple levels, right? The first level is source and then main and test as we had before. Java as we had before. But now we have this edu, odu, cs, cs330 set up here. Now in Java, it's considered poor form not to put your code in packages. Now the convention in Java is to make it the name of your institute, your top level domain of your institution. For example, cs.odu.edu is where I would start. Flip it. So cs.odu.edu becomes edu.odu.cs. Then whatever you want. So this is cs330 and this is examples. Now you can't exactly see the example at the end of this line, but it is there. So, and then the package matches the directory structure. So the directory structure corresponds to the package. So here, my board class is in the edu, odu, cs, cs330 examples package. My directory structure matches that. So as you can see, that matches /edu, /odu, /cs, /cs330, /examples. But my package and directory structure matches. Well, the two match. Now, we can see I've expanded this code base a little bit. And since I have board open, I'm going to start there. Now, I violated my class checklist in C++, and in Java, I violated it too. You can see now, I've expanded my pair class. My pair class now has an equals function. Right? If I'm doing some sort of comparison in unit tests, I would very much like to be able to compare two board pair objects without having to jump through hoops and rewrite the logic to do so each time. So I'm going to add a board pair equals function to compare any two arbitrary board pair objects. Now if I go through the rest of this code, should probably go up a little bit more. If I go through the rest of this code, I still have the character array, the board. I still have my default constructor. Get cell still the same. Set cell still the same. Get 3 cells still the same. Is full still the same. Board equals. Now I have a board equals. We're going to come back to it. Board toString. Now I'm technically violating the Java class checklist. I don't have a hashcode function, but that's a discussion for. But I'm violating the Java class checklist here. That's a good exam question. What's missing here? Hashcode. And clone, of course. Now, I want to be able to compare two game boards to see if they're equal, meaning two game boards are equal if every cell in both boards matches. And that's exactly what you see me checking here. First of all, I can't compare two objects if they're not both boards, so do that check first. Then, do my typecast, take that right-hand side object, and turn it into a board because I know it is, in fact, a board. And then I'm not checking to see that every cell is the same. I am looking for one cell that differs. Notice how I flipped the logic. For the two game boards to be the same, all of the cells must be identical. But I don't need to check to see that all the cells are identical, because I know I can flip the question and negate it. If any one cell between the two boards does not match, meaning if cell 5, if the center cell in both boards is not the same, the boards are not equal. I just need that one cell to not match, and that's what I'm checking here. I'm looking for that one cell that doesn't match. And I'm only looking for the first cell that doesn't match. I don't care if one cell doesn't match, 2 cells don't match, 3 cells don't match. I don't care if all the cells don't match. I care that at least one cell doesn't match. Because as soon as one cell does not match between two boards, they can never be equal. And then, if I reach line 159, I know all the cells are in fact equal. And I can stop. And now I have a full board class. I've added equals, I have toString, and I'm good to go. Now, if I look at game, you can see I've factored out referee. Referee is now a class in its own right. Facilitates testing, and referee became far more complete. So if I look at board pair. It's a very simple class, and it exists purely to store data as an implementation detail. And it exists fundamentally as part of a board. Referee, how many lines? Referee is 200 some odd lines. Yeah, I really shouldn't make that an inner class. That's just not maintainable. I should really keep that separate. And that's what I've done here. I've factored out referee. But the rest of game is more or less the same. Same attributes, same constructor, same play round, same get player, get winner, get loser. Same ended with win, ended with stalemate, is over, is not over. Same get board. Same round turn. So the game hasn't changed. All I've done is I've taken that referee logic and I've made referee a first level class. Referee is no longer bound to a game from an implementation perspective. Then if I look at the referee, well, the logic is, in fact, the same. Yep, this all looks to be the same. And then I'm done. So, the referee code is identical to last time. All I've done is I've taken all the referee code and moved it into a separate referee.java. It is now a first level class. It is no longer an inner class within game. And that just leaves us 2 files to discuss. Well, all I've done is refactor the underlying code, so play tic-tac-toe, that class has not changed. Player.java. Well, now it implements clonable, so I can clone players. I'm not sure why I have that space there, so I'm going to go ahead and in fact remove it. I don't like the fact that this is right here, so I should probably move that up, but I'll leave that alone. But you can tell I've fleshed out the documentation on all of that. So a player has a name and symbol. I have that reference Cylon still. I have that is generic check still. I'm not going to change to reference a different player. So possible Cylon, I won't switch to a different one while I'm working in this function, nor will I change that to a different player. Fine. IC generic. I fixed my violation of the rule of default constructors. So by default, the player's symbol is going to be a question mark until it's set to something else. Then same thing down here. Set the player's name to something I want. And then you can see the comment testing caught this, meaning how can I test for an expected character if I never set one? So I'm saying here in my documentation that when I call the constructor for a player, the name is set to either IC generic or a name I pass in, and the symbol is set to a question mark. And if I want it to be something else, I'll call set symbol later. Then get name and set name, more or less the same. Well, the same still. Next move, same as before. Is human, is computer, same as before. Get symbol, set symbol, same as before. I've added equals. Same logic for equals. Two players are equal if their names are the same, so I've had that all along. Hash code I've added. No, I've had that all along for player. Get the name, so whenever I want to turn a player into a string, I'm just worried about the name. I'm not worried about outputting the symbol. Clone, I need to be able to create a copy of this player. So a clone of a player is defined as a player with the same name. And I want the symbols to be the same too. So this is going to create a copy of this player where I have a second player with the same name and the same symbol. And then I'm going to return that copy. So this is equivalent to my C++ copy constructor. It's creating a new player, identical copy, same name, same symbol. And now that leaves one file once again. Packageinfo.java is not a class. It is a special purpose source code file in Java that allows us to document the package itself. So all of my examples are in this edu, odu, cs, cs330 examples package. I want to be able to write some documentation for that package itself. And in this case, I was very brief. This package is a collection of Java examples for cs330. Sweet, short, to the point. Or short and sweet, to the point. So now I need 1, 2, 3, 4 tests. This is just documentation, package info. This is just the main function calling everything, so I don't need to test this with a unit test. So now I get into my test code for everything. And we can see now I have one test file per class. And now I want to run my tests. So I'm going to create my jar file, and I'm going to run all my tests. And we can see I have two tests that fail. Test play round and test next move. And we're going to see why those fail a little bit. And now what I'm going to do is I'm going to reopen my Java results here. And because I set this up, I can just go ahead and jump into that directly. I'm going to jump into that directly. And I'm going to jump into that directly. Now I am doing a little bit of trickery here because I know the paths for everything because I set them up so I can do tricks like this. But now I have all of my test reports. So this is the nice thing about Gradle. It will generate all these HTML-based reports for us when we set it up with the appropriate settings and such. But if I look at this, this is example 5. And it's saying that, hey, my tests are 85% successful. 14 passed. Excuse me, I ran 14. 2 of them failed overall. That's an 85% success rate. Now, that's not a 100% success rate, which means there's a problem. And then I can see in a nice web report which test failed, and then the full stack trace from it. And the error is cannot test. That's an interesting one. So fine. Now my test coverage is far better than it was before. But overall, it's still not great. So let's go ahead and grab each of these. So board pair doesn't have its own set of tests because I'm testing it within board. It's part of it. So if I look at board pair, I'm not testing if it handles checking for equivalence to something that's not a board pair, meaning I'm never executing this branch here. If the right-hand side is not a board pair object, does this trigger and act appropriately? I don't have a test for that. I probably should add one. The board itself. If I look, get 3 cells. And I'm never testing that these assertions are triggered. Equals, same issue as before with the pair. I'm never checking to see that that branch executes. Checking to see 2 boards are equal. I'm never comparing 2 boards that aren't equal. So this has identified some flaws, some missing things in my test. So the takeaway here is when you're running some sort of test coverage tool or coverage tool, it can tell you whether or not your tests have covered your entire code base. So it can tell you whether or not your tests as a whole fully exercise your code in terms of every line of code is executed at least once. It cannot tell you if your individual tests or tests overall are complete and robust. And then player equals is the same issue for equals, and then I can't test this function for the reasons we discussed previously. So now let's actually look at our tests and how they're written. I'm going to look at test player first since I consider it to be the most straightforward. So because this is JUnit, I have a few more tricks I can exploit to make these tests far less repetitive. So I have 3 players, Tom, a Cylon, and the Doctor. And yes, the Doctor is a reference to Doctor Who. Now, I have this thing called a setup function. Now, this is a function that's going to be executed before every one of my tests. So every time I run a test, I'm going to have these 3 players reset to their initial state. And Tom's symbol is always going to be set to X. And this is going to run before each of my tests. So first thing I'm going to check. I'm going to check the default constructor. And now that a Cylon player, well, that calls the default constructor, so I'm going to leverage that. Now, if I look at this, that is a default player, which means if I pass him into the isGeneric function, I should get true back because he is, in fact, a Cylon by my definition. He is a generic player. And then, on a similar note, if he's a generic player, well, his symbol should be equal to the question mark because that's what the default constructor will set it to. And then I'm going to say, look, a Cylon has a different name from Tom. So Tom and the Cylon have different names. And I know that if 2 players have different names, they should have different hash codes. So test that a Cylon's hash code is not equal to Tom's hash code. And then I know that these 2 players should not be equal. That a Cylon should not be equal to Tom, or Tom should not be a Cylon. Fine. Then I'm going to test my non-default constructor. So first thing I'm going to do is I'm going to use that same Tom object before. I'm going to assert that Tom, when I get the string representing Tom, that I get Tom back. Or if I want to use the Hamcrest matcher, I would do the second line. Now, I would not include both of these in a proper test, but these 2 lines are equivalent. They check the same thing. As much as I would like to be, I am not the Doctor. It'd be cool to travel around the world, travel through time, solving things. Anyway. Then, once again, if Tom and the Doctor don't have the same hash code, they should not be the same player. Plus, the Doctor would absolutely destroy me in tic-tac-toe. So, I know for a fact that Tom is human, so that should be true. And I know that Tom is not a computer. So my default constructor test is incomplete. I should really have this test up there. And then, of course, these are not the Cylons you were looking for. I'm testing a Cylon to see, hey, a Cylon should not be true. So really, if I look up a little bit, this is the default constructor. These are in the wrong place. That's much better. I should probably turn on Smart Indent. I should probably have that turn on automatically, but there we go. So this is more what I want. So the reason I moved that is a Cylon uses the default constructor, which means any test that evaluates that should be under test player default constructor, as opposed to down here. And it's obvious that we have a very large problem considering Cylons are now passing as humans. So let's go ahead and just prove to ourselves that I didn't break my test. So now I made a change to my test and they should still pass. So if I run this, All of my tests still pass. Good. Now I should really force them to rerun and recompile, so let's do that. So let's force a clean first. So what I should see is my tests should all still pass because logically that still holds. And if I look, the only 2 tests that fail are the same ones that failed last time that I said should. Fine. Now I'm going to test set symbol. Now in our case, we have defined that 2 players are the same and their hash code the hash code for a player is based on the name. So if the name remains the same, hash code stays the same. If the names are different, hash codes are different. The symbol has no bearing. So I'm going to test set symbol. Now when I call this function, first thing I'm going to see is I'm going to get the old hash code for Tom. And then I'm going to test and see. Look, when I change Tom's symbol to something else, does the hash code change? Does the symbol change? And I'm just going to change it twice. Now, this test is incomplete, but it is a step in the right direction. I'm not fully answering the second question. When I call set symbol, is the name left alone? So this test is a step in the right direction, but it is still incomplete. If you're interested in the methodology and the full methodology and writing full, complete, good tests, take a look at the CS350 JUnit 2 discussion. But this test is a step in the right direction. It is not a complete, nor is it a robust test. At best, all these tests together are worth a B-, I would say. Until I complete them, of course. Test set name. Well, if I change the player's name, the hash code should change. Now, once again, I took this a little bit too far. I really only need to do these 3 lines right here. But, you know what? Good. So initially, the doctor's name, I'm just going to use the title of the doctor. And then I'm going to switch the names through a few of the actors who have played the Doctor 2005 and after. David Tennant, Matt Smith, Peter Capaldi, and Jodie Whittaker. Excellent actors. Excellent actors. But the point is, if anytime the name changes, the hash code changes. And the change in name should be reflected when I call get name. When I retrieve the name, it should be exactly what I changed that name to. But once again, I can't complete these tests because I have no clone function. But without a clone function, you can't test equals. Now you can see I'm sort of contradicting myself here because we know that it's line 104. We know that player has a clone function now. But the reason I added that is because when I was writing these tests, I realized I couldn't finish. So I wrote these tests random and said, I can't write complete tests because I did not implement the full Java class checklist. And that's why these tests are not complete. Because when I wrote them, I didn't have the full Java class checklist, which means I cannot fully answer that second question. I cannot fully answer, did this piece of code do something it was not designed to perform? I can't answer that until I have equals, clone, and hash code functions. And then after I added the clone function, I wrote a test clone function. So, the original, if you will. Go take the doctor, make a clone. This can be the original, if you will. And the original doctor's name was, in fact, William Hartnell. The first actor to play the doctor a long time ago. But when I make a copy of the doctor, his hash code should stay the same because they're identical copies. Both doctors should be considered equivalent because their names are the same. And I made a copy so their symbols should be the same as well. As soon as I change the name, however, the 2 doctors are not considered equal, and now the 2 doctors aren't equal because of wibbly wobbly timey wimey. That's a Doctor Who quote. Yes, that's a fun one. But I'm going to cut back on the sci-fi references. And then I get down to the function I really want to test next move. And I can't test it. So I'm just going to hard code a fail. Fail cannot test. Now this is a function in JUnit test that says, look, force the test to fail. I cannot write a test next move function. Can't write it. Because I hard coded the use of systemin in player.nextMove. In C++, I hard coded the use of standardin. In Java, standardin is system.in. In C++, it's cin, as we know. But until I restructure next move, I cannot test it without jumping through hoops, and I am not willing to jump through those hoops. Mainly because next move is itself fundamentally flawed. So let's take a look at another test. Referee. Now let's go ahead and rerun these tests real quick. Just going to run these tests and same results as before. Now looking at the referee, it's exactly what we expect, mainly because we just looked at it. But what we're interested in is not the referee, but test referee. So first thing I'm going to do is, to test the referee, I have to have a board. So there is a dependency there. So this is really more of an integration test, I would say, technically. But I'm going to set up, before each test, a brand new empty board and a brand new referee. Empty board and a referee. Now, I'm going to test the referee constructor. And I'm going to say check for win is 1. Now, if we look back at check for win, we will know that we will find that check for win returns 0 if neither player won, 1 if player 1 won, and 2 if player 2 won. So this is how we're writing the test. If the game has just started, I would be very surprised if either player has won. And I want to make sure that the player selected cell is empty function. The referee selected cell is empty function works. The game just started, so I should be able to recognize that all the cells are in fact empty. Check for horizontal win. Well, I'm going to pick one specific condition, the middle row, and I'm going to check to see. If the middle row is all X's in the board, and I pass that board into a referee, does that referee first and foremost recognize that those cells are not empty, and does the player in fact recognize that player 1 has won, because X denotes player 1. Then check for vertical win, much the same logic. Check for diagonal win, much the same logic. Referee's a bit of an odd case here, because referee is really a utility class. So that's that. Test game is a little bit more fun. So you can see I have a couple players again. I'm going to set up my 2 players, my board, and my game before every test. I'm going to test the game default constructor. When I construct the game, when I get player 1 back, player 1 should be Tom. Player 2 should be a Cylon. Tom should have the symbol X since he is player 1. Player 2 should have the symbol O. The game just started, so it definitely should not be over. Well, when I get the winner, the game just started, so there should not be a winner. I should get null back. Same thing for loser. And the board should be empty. And this is why I added the board equals method. I cannot compare 2 boards if they are not both equal. And this avoids me having to write that loop to test to see that the board is empty. Because within the equals function, that check's being performed. The equals function tells me whether or not the 2 boards are the same. And I can't test playground. I can't continue this test. Because player next move, play 1 round, these are all hard-coded to use system in. And because of that, without jumping through hoops, I cannot complete this unit test suite for game. And then test board is going to be our last one. So you can see I've moved expected empty string up to the very top. I'm creating my board and I'm recreating an empty board before each test. I'm going to test this default constructor. When I have an empty board, every single cell, starting with the first one, should be 1, then 2, then 3, then 4, then 5, then 6. So if I go through the board, top left, each row, one by one cell, it should be 1, 2, 3, then 4, 5, 6, then 7, 8, 9. Then, this is me checking the get cell function works correctly. This is me checking that the toString function works correctly. This is me testing that the board is not full. Then I'm saying here, well, I want to get 3 cells, the first 3 cells, and I would expect to get these 3 cells back. The first board pair, 0, 1. The second board pair, 1, 1. The third board pair, 2, 3. In an empty board, that's what I would expect. So, is my first retrieved value equal to my expected value? Is my second retrieved value equal to my second expected value? And is my third retrieved value equal to my third expected value? And once again, I started counting at 0 because I'm a computer scientist, right? And we all know we start counting at 0. Then I'm going to go down and I'm going to test set cell. And I'm just going to pick 2 arbitrary cells, top left, bottom right. I'm going to check that both those cells were set to what I expect, or what I expected, yeah. And I'm going to check to see that I get the 3 pairs I expected back. If I get the 3 pairs on the diagonal, top left, middle, and bottom right, I expect the top left to be X, the bottom right to be O, and the center to be 5. And same check as before. And then I should no longer get the empty board output back, so it should not be equal to the expected empty string. The board should no longer be empty, so the board should not be full. Well, yeah, definitely the board is not empty and the board is also not full. I've only filled in 2 cells. So the board should still be not full. And then this is the board I expect to get back, where X is in the top left and O is in the bottom right. And yes, this guy right here is an O. And that is the end of our unit test here. Now, these unit tests are not complete. This is a first step in writing these unit tests. I would need to go through a couple more iterations first to say these are complete. These are by no means complete yet, but they are far better than what we started with. Now, if you've been following along, you've been paying attention, you will notice that there is one more example. Example 6. Now, examples 1, 2, and 3 were C++. We just went through examples 4 and 5 that were Java. And that leaves example 6. And example 6 is Python. Now, we've already spent about an hour, 40 minutes discussing the Java version. I think now is a good time to end the discussion and make the Python one a second part. But I want you to think about just how similar C++ and Java are and how much of that code you understood based purely on what you know of C++.